I hope you enjoyed your meal, and now you have some more time for me to hear something and give me the chance to say some words for you. To you. First of all, it's a pleasure of mine to be here in Ukraine. It's the first time I visit this country. Thank you to the organizations for all what they have done to make this school live, more or less to say alive, bringing you some more words about the options of biomedical things, and as well as for this industrial artificial intelligence, for example. From my background, I'm a mechanical engineer in informatics. I'm studying some 30 years ago, and I made a lot of work in that direction over the last 30 years in automation technology. So first of all, I would like to explain something about artificial intelligence as we use it as a future technology for our one's future. For the last 70 years, it was also a scientific technology, of course. In the field of industry, especially I'd like to show you something about my own field, or the field of my research team in focus of predictive maintenance of multi-vendor heterogeneous machineries. And okay, it's nothing to do with this normal school here, what you follow now over the week, but all of the robots you are using and so on. There is this kind of machinery that would like to give them the life over the lifetime for the usage for you, and so I would like to explain how we can do it in the future term to use informatics, to use information technology in kind of artificial intelligence. So first of all, some introduction of mine, what is the background and what is the schooling about this field, what Marcus was mentioned. This group of professors at the university ground, and then we go in my own field of cyber physical things before we can go in further with the artificials for these multi-vendor systems, especially for predictive maintenance applications. So latest and the conclusion. Just to have in mind, I'm going with this field of automation over the last 30 years around. And starting at the Production Technology Center of the Technical University of Berlin with this ideas to use robot systems to make some systems, some processes automatically, especially to disassemble, for example, some washing machines, what we see in here, some machinery who gives us the information. Here, please take your seats. Well, and so you see also some 30 years ago, there was something that we're using information to make some decisions for the next process steps inside of machineries. Later then, I'm starting also my own companies in the years 2000. I'm starting some 21 years ago, with special mechanical engineering, where we produce also machineries, design them, construct them, and bring it into the usage at our customers. And we are using also 20 years ago the internet to collect informations, to make some decision of them, and making also some prediction. What could be happening in the next future? So that was also 20 years ago, but we have no artificial intelligence. It was just some rule decision processes, some models, some data-driven models we were using at this time. Later then, I'm starting 10 years ago with my career at the Technical University in Wildau, where I'm in charge of the field of automation technology. We were using the informations to bring up everything in a new step for these machineries. We developed and built up some worker assistant tools. We have some robot systems with us. We have a test bed where we use artificial intelligence and where we use, augmented reality, I would say, in a field where we have production and logistics machineries to be used, and we added some more information of the process to the workers as a worker assistance system. We have also development environments where we can make, for example, our own processes available to build up, for example, some quality procedures with this information and with artificial things then to be used. And finally, we have also an intralogistics laboratory where we have also stock systems and autonomously driving systems, for example, with self-prediction through the shop floors as usable application, for example, also for the teaching for our students to see how it is possible to use the information itself and how to realize and make some planning for the next passes. So what Markus explained that I'm starting a field or a group of colleagues at the Technical University playground, more or less to say, some years before. It's correct. We had in the year 2019 the research year, the topic of this research year of artificial intelligence in Germany. So we were asking, what is our university doing in that field of research? And so we asked in the groups of both faculties. I think Markus has explained anything more about our university, I would say. And so I'm asking who is doing something with artificial intelligence. And so we got a group of 14 colleagues of mine. As well, we are now 16 because there were two coming additionally to us last year. And so we're starting a Wildau network of artificial intelligence where we have over the whole value chain from the human resources department, over the law department, where we have also the economics with us, we have the industrial engineering, we have the mechanics, and so on, and automation, of course, as well. Who's doing everything together to give a chance our customers, our partners, industrial partners in the region of Brandenburg, to ask the process to support by all ones. And so we are very strong together. We have over 50 scientific employees, research assistants, more or less to say, who can dealing all these things with the artificials. And so we have different kind of options from the quality insurance until we go into the step how to make the autonomously pass controlling through the shop floors between our tools, for example, to produce something from some goods, from the raw material to the material we would like to get from the process itself. Well, we are starting, and now we're doing that's why that we get in partnership with our bigger companies of these regions. So maybe you heard from Markus that the Robert Koch Institution has made their own institute for public health, artificial intelligence in public health with us in Wildau. So he's one of the partners now from this scientific way, also with our network in Wildau itself. So from my profession, as I told you, I'm a mechanical engineer and informatics scientist. I'm doing a lot of teaching, for example, modules in this field of cyber-physical production systems. And that is because we need something where we can do all the processes later than more efficiently as we have it at this time. So that we can expect that the aims that we're facing for the future, especially in our global world, are following these 5 points. This mass customization, where we get the individual good from our producers, as well as we need to produce them in a collaborating system and on an adaptive way in some aspects of modularized machineries who can communicate point to point. Point to point means in that way that every entity and every technical entity in the machines are able to communicate each other to make some, or to give them some informations from the processes to the other ones who likes to make some new decisions from it, for example, for maintenance. If you have a tooling machine, for example, or you have a robot system, maybe also from the screen laboratory Marcus is working for, and this robot system has some motors included who get some information about the consumption of energy what they use, and the consumption will be increased over the time. So the process could be say, yes, there's something happened. There's something what we have to check, we have to inspect, whether there could be something wrong in the future. So we need to maintain this procedure and to send persons to them, employees to them, to avoid this problem. Therefore, the point-to-point communication from the sensor to the planning systems, to the machinery itself, needs to be point-to-point. There is nothing else, nothing other server or something else in the middle of that. There needs to be the decision of it, and that is what we needed to make these procedures available and suitable for the whole process. So what? So that we can say, maybe you heard, I'm very sure that you heard about this Industry 4.0. This is some buzzword over the last 10 years. And this Industry 4.0 is based on the cyber-physical systems itself. And cyber-physical system means it's based on the other side on this industrial, on this Internet of Things, I would say, this Internet of Things, what Kevin Ashton was programming in the 1999 on the MIT, so some 22 years ago. And this Internet of Things is necessary to have these informations from the entities itself. So we are doing a lot of everything what we're doing on this based on this IP addressed IP used machineries and informations. But there needs to be exchange informations to optimize maybe also themselves or make the analytics of them. So that we're using, because we are not alone by ourselves in the industry, so we are part of the network from our supplier, by our own, and the other ones, the customer, who like to use also our products, our industrial products. And because we have now the options of cyber-physical things, we can make other points or other services, for example, or new business ideas to follow. Maybe you see here one example. So I would like to give it to you, that we use digital data as a material for our services. Maybe a small project, what we were following is that we have, for example, the company Rolls-Royce with us in DAAD German-Ukrainian. They're producing turbines for the aircraft that we heard about, and these turbines they were sold over the last years just as a product. But they started 3 years ago in the year 2018 to sell not the product itself, to sell the service of this product, for example. So as an airplane producer, you are not selling, you have not bought the turbine itself, they just bought the service to use these turbines. And that they can do because they have this turbine as a smart device to be run. The smart device means every 2 minutes, every 3 minutes, they send information from these turbines to a server system, to a decision-making system, to prevent that these turbines will be wrong, will be damaged over this time of usage. And that kind of services they use then as a smart data to optimize, for example, the use of these turbines and the services to leave them in a usable stage, in a suitable stage inside the usage of these options. Well, and to do so, we're using especially also artificial intelligence. For example, to make this predictive maintenance procedures suitable for the customer and for our ones too. So, and if we see this advanced applications, if we see the options, what we can do in the industry. So, everybody of you have heard about this autonomously driving. For example, you see the points from Google or the other supplier who sent us these cars, and perhaps they want to meet each other to the other ones, have some problems at the moment, but there will be follow-up in the next 10 years, 12 years, 15 years, that you will find them on the street. We have the first buses, for example, also at the in Berlin at the Tegler Forst on the street, and they bring the persons there autonomously with path planning and also localization as one of the parts that are used by artificial intelligence to be run. The other ones is for quality control. We're doing very often that we can, for example, detect some points what is not maybe as a food usable. You have some information, then it's a stone, for example, bring it out, or our pizza is not very well equipped, more or less to say, with some salami meat. As well as we have some plant optimizational things, especially in the field of the oil industry. We use it at the PCK, this is a treat, as an option, where we bring out the flow through the pipes in a very well procedure. The plant optimization is one of the things. And the other one, and I would like to talk about it a bit later, is predictive maintenance, for example, of this kind of heterogeneous machinery. Means if you have one machine and you have a process with different kind of machinery be used. So how to use, for example, the same module, the same data-driven module for prediction from one machine to another one. I would like to explain a bit later, so that we see then the predictive things that can then decide whether the product, whether a part of this machine could be damaged in the future, or can be out of usage, and so the machinery stopped, for example, for a while, and this downtime has to be prevented, more or less to say. In industry, of course, we have some more things to do. We have these points of chatbots for data protection, as what is written there, etc. It's everything an option to be used with these artificial intelligence. So, well, if we see in the heterogeneous parts, so we have the point that we need with this predictive maintenance procedures, the subtasks that we need to detect what are the anomaly, what is the anomaly of some parameters on a domain, what are the different features you would like to calculate, and to see what is from the normal case another anomaly failure. What could be then, well, it's not in a failure at the moment, it's just an anomaly to see then whether it crossed the line or needs to be identified. The other one is, okay, something wrong. That we have, for example, then the point that we analyze that we have, if we have detected this anomaly, then we need to decide whether that could be a defect or not. And this defect diagnosis is something what we're doing also with predictive maintenance as well. And we use it then, especially in that kind, with artificial intelligence, to interpret them, or to determine how long it could be still remain for this process, or it needs to be unfix this problem, means it needs to be give some predictive inspection, as well as disassembly and assembly with a new material, for example. So it could be also, for this useful life, necessary to determine the remaining time for this product. So as motivation we have now is a point that these fault diagnosis needs to be automatically be done to increase the time of machine usage in the process itself. And this plays in that way a key role for this maintenance strategies we have now in the industry. The automatic fault diagnosis is the point. And as we see, there are two different approaches, or two different modules usable for fault detection and diagnosis. The one is the data-driven approach, and the other one is we have model-based approaches to be usable. So it is almost better to have the online status, we have the condition monitoring, the condition-based monitoring of this data, and it seems to be more applicable if you use them. Okay, that is something what is known over the last 2 decades, 20 years. But what is new now is these heterogeneously machines. This heterogeneously point is that when we have a process where we have, for example, just one of machinery we used, for example, bigger machines who are just producing one time, and they get the failure, and you have to change this machinery by another vendor, by another supplier. So you cannot use the same model, for example, for the other machinery, what you use again now. So what we need is that we have for these target systems, before it was a source system, as we have it learned to our AI. If we change this product to another type of it, or just another vendor, so these data from this target system are not available. And how we get this possibility to change this machinery to each other and get the same models runnable on these AI without knowing what are the effects have what are the data of the effects of the faults. We get some deep information from the machines, but we do not know how to use them on this to decide for this detection of the fault itself. And so we need this data-driven fault diagnosis model, especially to transfer this knowledge from one machine to the other one without any new learning procedures in this field, in this working field. How to do it? So what we can do is in that way that we use the option of transfer learning. Is we have both option of supervised and unsupervised learning. And what we are doing is to use this reinforcement, and that we take this transfer learning procedures from one source machine to the next target or two target machines. We have just one source. We pre-learn the module itself as data-driven model, and can then this module used on different kind of target domains. So here it is written, though we have this training data just by this first source module, and from this trainer data we make then this feature extraction. This means then we know there are different kind of features, of course, in each machinery we used, and we take our model, train them. Unfortunately, it's not my laptop, therefore it is not so well written in this way. Then we have some module evaluation, and last but not least, we get our machine learning module for these target machines later then. And that could be that is our hope, that is our aim, that we can then use this machine learn ML module on different kind of targets, not on the only one. So if we train this for optimization for this module, so then we get this module for machine learning for these multi-vendor machineries. So we can then still, at the end, take just the right side this one model with different kind of machinery used. I would like to show it right soon for some chilling systems, some refrigerating machines. This is our aim or our module, what we expect. Okay, this is just, I do not know what came as the next slide. So if you see it here in that situation, that the most important thing is what we have in the lower section of this slide, where we have the condition-based monitoring written to the current condition we have in the machines, and about this extraction, if we come from the raw sensor data, especially in this fault classification procedure, this is the most important for our ones. So we detect the faults from this anomaly detection, and then we need to isolate this fault and give them in some kind of identification, so that we can then afterwards make the decision of them whether the procedure could be followed up or will we go into a situation what we need to, for example, work down or make this procedure down. So to prevent, for example, any kind of difficulty to the process itself. And the position beside or behind the current condition, going then in this prognostic and health management module, what we have here, where we get then this predictive faults to evolve inside the procedures, and can give then after the latest the schedule when we can make, for example, the actions in the future, for example, based on this information. So if we go in there, if we go in with this concept, with this idea, how to get this condition-based monitoring, how to use them. So we were trying to make this on one kind of machinery, means in that way, a refrigerating system, very big ones. This is just one-off production system, it's just a single one each time to freeze up, for example, a bigger room for food industry or meat and vegetables are included. It's a very big system where we have a vapor compression system inside. You see it here for food industry as well as for chemical industry, where we have it right for the moment, of course, with the COVID-6, we need to have this minus 70 degree, for example. And that has to be the point that we have this high demand on reliability in the system. So we need to know when to stop, for example, when to bring it down, the system itself. So the capacity needs to be then, if there is something wrong, so it could be very, very difficult then for the good inside, of course, the rooms. We have a big room with these COVID vaccines. It could be very difficult if we lost the function of the machinery, of course. So we need to know when it could be happening. So therefore, we use these procedures, these modules, this data-driven model, especially for isolation and identification of faults. Very important thing, but it's based on a different variety and the huge variety of the system design of this one-of-kind machinery what we have there for this refrigerating system. And for example, also because we have a lot of a huge variety of operating conditions itself to be used. How's the temperature, how's the pressure itself, and so on. And so we need to have a solution where we can use this machine learning model what we have as a transfer learning model with domain adaptation, where we can take the parameters of the model in that way that it is usable then afterwards also on these other kind of maybe then also machinery of this refrigerating system. That we can expect, we can realize that way that we get the principal components of these machines. Because of this huge variety, we have around, I would say, 20, 30 parameters. We have to, and the interaction of them, we have to reduce this to mostly principal components itself. What could be most important for the process. So we have this so we have how to say, multi-component system where we have everything is with interactions, and we need just the most widely applied or this is algorithm, but we use just the core, the principal components then for our option to be divided then for the procedures inside the neuronal networks. So, well, if we go in that way, that we, for example, here bring from these component measurements to identify what could be then the correct outlier, the correct anomaly points to be used then. We take this unsupervised learning to cluster the parts itself, and could we then identify what is the anomaly that we like to then to find out as a maybe fault to be used in the module itself, in the modules. So we can later then choose this principle for this condition-based monitoring itself. So to identify the fault, to make then the decisions from this fault back. We have the maybe to see this domain module, data-driven module, where we have the source domain, where we get this stage for this refrigerating system, for example, from the Ashir module, what is very well known in the industry, where we get, for example, everything so produced that we have finally the fault classification, as we have it here as a detection firstly, and then classification here on the target domains for the training status, and later then for the domain itself, whether the usage. So identified that we can use it only one time to train the model itself with the source domain, and can then spread it to the target domains, it means the target systems, what we bring in just by use the data what we have from this historical, as well as then from this online data on the target domain is used in the process. So this is just the same to use if you have just this cloud of some labeled data, how to analyze then the principle, so we can just bring out this small part of this graph. That way that we have then the novelty described for the procedures and for this reduced variability inside the module. So finally, if we take our test system, so it is, we are working together with a company in Potsdam, near to our university, where we try to evaluate this idea. So we have, for example, this test facility. This is around 100 kilowatt chilling system or refrigerating system, where we try to identify the different faults that we have. For example, this points from the parameters from the process detected. And then we try to isolate the anomalies that way that we have then, and defect in the, for example, vaporizer as well as in the compressing system, compressors where we have the different speed of the compressors as one of the feature what needs to be monitored. What needs to be monitored the different kind. Okay, here the faults and written here. We have this reduced condenser water flow. We have the water flows also in the evaporator, as well as the most important thing is this oil retention, where we have to see then whether the tubes are still usable or not, so that we, if that feature is not well equipped, so then we have a capacity loss of over 30%, 30-40%. Without a disturbance seen is just you need more, for example, consumption of energy to have this machine still under processing. And finally, we make a lot of experimental investigations of it, so that we can then afterwards try to, or we can decide that if we can reduce the parameter cloud, so we can we are able to express the option that we can find the fault very easily, in that way that we define just the points of water flow on the evaporator, as well as to consumption with the speed what we have here for the rotational of this compressor. That way that we have afterwards the decision that if they get to a grade who is as who going further to an extraordinary point, so it could be then decided there will be a fault very clear, very shortly expected, so that we can use it as a classified fault. So in support vector machines, this is what we have here as a classification module, as a classification algorithm. Reduce, for example, also the amount of different features to give us then the variety of these anomalies in the, for example, in this different kind of approaches for the detection itself of the faults. It's called vector machines. So we get then finally the conditional distributions, means how to turn, for example, also the different views on the targets, on the parameters, measuring inside the usage to make the adaptation options, or make, for example, also these detection very easily for the process itself. So finally, just for this moment, we have, as I explained, the different kind of domains. We have some source domain and some targets domains to be used. The source domain would be used, the teaching, these parameters itself came up from the shear system, what is well known as the centrifugal chiller system. They are very well known, this labeled data. And we trained the module itself to making then afterwards this decisions available. And then we used this module and get it on a target domain, what we have, what explained there from this Potsdam company who realizes as a screw chiller here with us, and will reduce with this transfer, or with firstly with the your mind. Finally, we reduce the parameters, we reduce also these features itself in that way that we have, for example, only this K, only with 20 core significant parameters, we can then calculate the fold score. The fold is the fold in percentage of 90% as a prognostic view on the process what we have run on the chillers. So if you see then under these different kind of features, maximum 20s, that we can get this fold and prognostic or detection, prediction of this fold. We have here for refrigerant lags or reduced condensed flow in a prediction of around 90%, 98% in maximum if we have this advanced transfer systems available with this supervised learning procedures. So as a conclusion, we were trying this, we bring now this model to different other targets. Means we're using now in the field this module on 4 different other ones, chilling systems, and we found out that we have this cross-domain full diagnostic very successfully on these different types to be used, and it will be also then as an achievable proposed module for other machineries than we used. We see this with these robots, and that will be also be done over the next years, over the next, hopefully not years, also at our university. So within the next year, we will finance, we will investigate it, we will invest it in a big technicum for artificial intelligence, where we have also some robots included, and we can then bring this prediction module also insert in our system. So it was very roughly just the idea for prediction in the maintenance procedures of our industry, and some other ideas in that kind. Finally, I would like to invite you also to come to us. You can see us also in Wildau some years, some months, sometimes in the next future. For example, we make every year some called, therefore it was just this pictures also with some international groups also of students with us in Wildau, some kind of regatta races for the solar boats. I would like to invite you maybe also to build up such kind of boat. We use it also with, hopefully for this energy consumption of this boat, we would like to also bring in some artificial things inside. So that will be then also in the future. So for that moment, thank you very much for the attention. If you have any other questions, please let me know. Yeah, well, please.
Thank you for interesting talk. My question might be not about the topic, but you mentioned that you have a group working on artificial intelligence in public health. Can you tell which tasks they solve and how to commercialize that research on the field?
Actually, I'm not the researcher in this public health. It could be that some of Marcus' team or something else could be then be made there, or maybe also with Heike. Do you have some public health research? No, not in the biomechanics. I don't know exactly. I was
not in my group, but
maybe Marcus. What I was talking about, I was trying to talk about, was the Robert Koch Institution. With the bigger ones in Germany, who's dealing with all this kind of and they built up a research group at our campus. 130 researchers will be means they're starting in the earlier summer this year to build this whole procedure. But up to now, as I know, there is nothing to be visited. They're starting to prepare everything. So at our university, as I know, there's no public health researchers in there. But as
sometimes we have some health data analysis, some statistics, but no mechanical.
No mechanical. Thank you. Okay. No other things? No other questions?
I was just interested, can everything it works with just solar energy, is it enough?
I'm sorry?
Like, can all these machines work only with solar energy? So I'm just thinking about if we are going to industrialization or something like this, can it be like in harmony with environment? I mean, with the code.
No, it depends. Your question is whether this machinery could be used by solar energy
Yeah,
only.
yeah.
So it depends a bit how many current you can earn from the solar fields you have, right? I think this at the moment is still too much to have everything runnable with solar energy at our Earth. Otherwise, we get we have so many capacity from the sun coming down to our Earth, means about 70 terawatts per hour. That could be enough, but you need to be then have everywhere these modules be usable. But for the machineries from this refrigerating, these chiller systems, this is not possible to use. Just for smaller engines, for example. But thank you very much. Still one question.
Yeah. How to prevent some troubleshooting with artificial intelligence in the controlling systems? So maybe they can make a mistake and we obtain the wrong results, or how to avoid?
Do you mean to teach the modules they make a problem or failure?
Maybe like
by using the machines, they make some failures.
yes, with machine using. So what's the second stage of the safety to prevent troubleshooting of machine? So it's like a two-stage safety model we should use.
As this module, what I would like to, or what I express, or what I explained to you was just for the automatically use of machines without any human inside, as a human during the process itself. So there's no, so there's new disturbances from these humans to this process itself. As I really understand what you mean, is in this troubleshooting after the fault was, or the failure was expected or was came up, or so how to prevent this. In any case, if you know before that the failure could be happen, the failure could be maybe in the next few days, months, or in time period happen, you can bring this machinery in planned downtime. You can bring it then in that way that they will be going off, for example, in a shift where no human are with us. So it could be then prevent also that this troubleshooting would be very, as this procedures of inspection and to maintain the machine could be then in that case very secure itself for the persons what they has to be needed. This is not an accident in that way that the failure will be happened. For example, in PCK, it's a big refinery in our Brandenburger suburb, not so far away from the border to Poland. They have a blackout some 4 weeks ago, where the consumption was be break down and the whole refinery going down. And that was really, really hard for the machines itself, because not because for the pumping systems, for example. I see it 2 days before. I've seen these big pumps running. The problem was, as the current was not with them, the chemical process going out of range, and so everything was then in that way that the ceramic going wrong, and everything was broken and damaged. And that was an accident because of somewhere or somehow, in that way, it's just a person who makes a wrong connector. He pushed the button on the wrong way, and then the whole region, 40,000 milliamps going out of current. So it means it was really a hard accident what they had there 4 weeks ago.
And how I understood, this machines can learn like with artificial intelligence, right? So if it will be some mistake, it can recognize it and just solve the problem by itself, right?
Later then it will be in that way, that the machines itself will be analyze these failures or these possible faults, but we can then, first of all, they analyze the anomaly, and then they identify that from this anomaly it could be a failure. And if they know that it will be a failure, they can then prognostic, as a predict and making a decision process to, for example, to ask somebody from this maintenance team to come over to check whether what has happened or not. And though this failure could be then prevent, that it will be not happen then to the machines. Well, that way.
It's no more questions. With that, I would like to invite you cordially thank to Professor Dr. Reiff-Stephan for your interest, for your participation, to take part in our in-person event in this challenging time. And also I would like to thank the participants from the Technical University of Applied Sciences, also as we have the biggest team from our university, and I would like also to underline the high amount of people with German origin from our university. So thank you for your kind support also of organizational questions. So with that, let us cordially thank.